Hi, my name is Randy Appel, and I'm your Regents tutor. And in this lesson, you're going to learn everything you need to know for the Regents on atomic structure. Now, the first thing you need to know when you're dealing with atomic structure is the history of the atom. How do we know what the atom looks like? And what the Regents ask you to know is they ask you to know that the atom and the history of the atom has been discovered by many scientists over a long period of time. It wasn't one person who came up with this one experiment and now we know what the atom is. It was a lot of different scientists with a lot of different experiments all together make up what we now know is our atom. So that's the major history aspect. There are a lot of different experiments, but the one experiment you need to know more than any other experiment for the Regents is Rutherford's gold foil experiment. Rutherford's gold foil experiment is the most important experiment, and you can't know the Regents and atomic structure without understanding it completely. So we're going to go over it. First thing you have to know is what Rutherford did. Rutherford took alpha particles, and you can go to the concept on alpha particles if you want to learn more about what they are, but for this experiment, you just need to know that an alpha particle is a positively charged particle. Rutherford took alpha particles, positively charged particles, and shot them at gold foil. What is gold foil? It's just gold. It's gold atoms, many gold atoms. That's what makes up gold foil. Just like in your kitchen, aluminum foil is made up of many aluminum atoms. Gold foil is made up of many gold atoms. So Rutherford shot alpha particles at gold foil. That's what you need to know first. Then you need to know what happened. Well, the first thing that happened, and the most predominant thing that happened, is most of the alpha particles went through. Most of the alpha particles went right through the gold foil. Now, what did it go through? Well, it went through nothing. It went through empty space. So because most particles went right through, Rutherford said that the atom is made up of mostly empty space. So that's the first thing you need to know about this experiment. And the second conclusion they came up with was some of the particles, not all of them, and very few of them actually, but some of the particles that didn't go right through actually got strongly deflected. They got pushed back, and you can see this happening in the slide screen. Why did some of the particles get pushed back? What deflects a positively charged alpha particle? Well, a positive charge. Positive repels positive. Opposites attract, and likes repel. So what repelled the positively charged alpha particle? Something positive inside the atom. Now, it only happened in very few of them, so we know that this positive charge is very small. We now know that the positive charge that repelled those alpha particles was actually the nucleus. So we learned that there was a positively charged nucleus in an atom from Rutherford's gold foil experiment. So to sum up Rutherford's gold foil experiment, we learned two things. And you have to know what he did, what happened, and what did that mean. So what he did, he shot alpha particles of gold foil. What happened? Most went through, which told us the atom was mostly empty space. What else happened? Some of the particles got deflected. What did that tell us? That there was a small positively charged nucleus in the center. So that was Rutherford's gold foil experiment. The modern model of the atom is a little different than Rutherford's gold foil experiment because Rutherford didn't take into account the electrons and where they were in relation to everything. So the current model, which we call the wave mechanical model, shows the nucleus in the middle, positively charged nucleus in the middle, with the neutrons also in the nucleus, and the electrons are actually outside the nucleus in this big cloud of electrons. We don't know exactly where the electrons are, but we know that the electrons are surrounding the nucleus in a cloud of electrons. Now, the region where the electrons are found within that cloud are called orbitals. The orbital is defined as a region of probable location. So are electrons in fixed circular paths? No. Electrons are in orbitals, which are regions of probable location for an electron. And that's the current model, the wave mechanical model. Okay. And the last thing we have to talk about with history, and the Regents likes to talk about, our knowledge of the atom has changed over time, because it has changed. First, way back in the day, Dalton, and you don't need to necessarily know it's Dalton, but you need to know that he proposed that the atom was a hard sphere. Okay? It was a hard sphere. There was nothing, it was indivisible. You couldn't break it apart. It was a hard sphere. So we initially thought it was a hard sphere. Then we thought that the atom was mostly empty space because of Rutherford. And now we know that the electrons are actually in orbitals surrounding the nucleus. So that's how the history of the atom goes, and you need to know that. The next thing you need to understand are the subatomic particles. Subatomic particles are very important, and in this case, you need to memorize them. You should have these, you should know these just like that. The subatomic particles are protons, neutrons, and electrons. And there are three things you need to know about the subatomic particles. The first thing you need to know is the charge. Well, protons are positive, pp, protons positive. Neutrons are neutral, NN, neutrons are neutral or no charge, and electrons are negative. Well, En doesn't really work, but you just need to know that electrons happen to be negative. So that's the first thing, charge. Protons positive, neutrons neutral, electrons negative. The second thing you need to know about the subatomic particles is the mass. The mass of each of them. A proton has a mass of 1 AMU, and an AMU is just an atomic mass unit. It's how we designate the mass of the subatomic particles. Protons have a mass of 1 AMU. Neutrons have the same mass, a mass of 1 AMU. Electrons, however, have a mass of almost 0. Electrons weigh much, much, much less than a proton or a neutron. It's actually 1,836 times less. You don't need to know that, but you need to understand that protons have a mass of 1, neutrons have a mass of 1, and electrons have a very small mass, which is basically 0. And the last thing you need to know about the subatomic particles is where they're located. You need to understand that protons are in the nucleus. Neutrons are also in the nucleus. So the nucleus, which is very important, is composed of protons and neutrons. And you also have to know where electrons are. Electrons are found outside the nucleus in orbitals, or regions of probable location. Those are all memorization. Now, let's say you get to the regions and you just get scared, and you forget the charge and the mass of all these particles. There's good news. There is a reference table. Reference table O, as you can see on the screen. Reference table O shows not the location of them, but it shows the mass and the charge of all the subatomic particles you need to know about. It shows some more particles, but we're talking specifically about protons, neutrons, and electrons here. So you could see on table O, it says beta particle. Well, beta particle in parentheses, it says electron. So that's an electron. You also see it says proton. It also says neutron. Now, how do you recognize what the mass or the charge are? The top number on the notation represents the mass. And the bottom number on the notation represents the charge. So you see the beta particle, or the electron, has a top number of 0, which has no mass, and a bottom number of -1, which has a charge of -1. You see a neutron, a top number of 1, which means the mass is 1, a bottom number of 0, which means the charge is 0. Neutrons have no charge. And finally, protons, you see the top number is 1, so the mass is 1, and the bottom number is 1, so the charge is +1. And one important thing to note about the charge of the electron and the proton, they have equal but opposite charges. The charge of an electron is -1. The charge of a proton is +1. So they're equal but opposite charges. And that's the subatomic particles. I want to spend a little time talking about the nucleus and its charge. The nucleus, you need to understand, has the protons and the neutrons in it. Now, what's the charge of a proton? Positive. What's the charge of a neutron? There's no charge. Since those are the only things in the nucleus, what's the charge of the nucleus by itself? The nucleus must have a positive charge. Well, how do you know how positive it is? Well, let's take carbon. Carbon, I'll tell you now, but we'll talk more about why. Carbon has 6 protons in it. And if it's a carbon-12 atom, it has 6 protons and 6 neutrons. Okay, and we'll talk more about why that is later. But since it has 6 protons, it doesn't matter how many neutrons there are, because what is the charge? The charge is the only thing that has charge. Protons have a positive charge, neutrons have no charge. So what's the charge of the nucleus of a carbon atom? The charge is equal to the number of protons. So the charge of a carbon atom, of the nucleus of a carbon atom, is plus 6. So it's important. The Regents a lot of times asks you for the nuclear charge, and now you know how to find it. It's just equal to the number of protons. Okay, now we're going to talk about some definitions that you need to know. Very important definitions. The first one is atomic number. The atomic number is equal to the number of protons. But the atomic number is even more important than that. The atomic number tells you what elements you have. Let's look at the periodic table for a sec so we can figure out what I'm talking about. We have the periodic table over here. And you can see it says at the top of the periodic table atomic number, and it lists them. So it's giving you the example of carbon. It has carbon up here, and it says the atomic number is 6. Now note, it lists the atomic number for every element on the periodic table, and you can see it's the biggest number in every box. Chromium is 24, copper is 29. Every box has an atomic number. That tells you how many protons there are. And that tells you what the element is. So carbon, for example, has 6 protons. That means that because it has 6 protons, that's what makes it carbon. Nothing else makes it carbon. Not the number of electrons, not the number of neutrons. The thing that makes it carbon is the fact that it has 6 protons. Well, what if it had 7 protons? It can't be carbon. Carbon has an atomic number of 6 because it has 6 protons, and that's what tells you what element you have. So it's very important to know the atomic number is the number of protons, and that's what tells you what element you have. Very good. The next thing you need to know about is not the atomic number, but the mass number. And the mass number first is defined as the number of protons plus the number of neutrons. Now, you should be thinking, oh, that makes sense. Protons have a mass of 1, neutrons have a mass of 1. Electrons shouldn't be in the mass number. Why? Because electrons have no mass. So protons and neutrons make up the mass number. And we have to tell you what the mass number is. The mass number is not on the periodic table. On the periodic table, they list the atomic mass, which we'll talk about in a second. The mass number is the number of protons and neutrons. And we designate that very specifically. We have to tell you what the mass number is. We don't have to tell you what the atomic number is. Why? Because if I say carbon, the atomic number is 6 because there's 6 protons. But the mass number is different. And I'm going to show you all the different types of notations for mass numbers. Let's say we have carbon, because we like carbon, it's easy to work with a mass number of 12. Fine. This is how we designate carbon with a mass number of 12. We could write carbon 12. That's carbon with a mass number of 12. Keep in mind, a lot of students get confused about this. This right here is not a negative sign. This is not a negative sign. This is not carbon negative 12. This is carbon with a mass number of 12. This is just one way we could designate that. Another way is we can write the symbol for carbon and put a 12. That's another way we could do write the mass number. There's 2 more ways. Another way is we could do the symbol, and we can list at the top left the mass number, and at the bottom left the atomic number. This is another way to designate mass number. By looking at that, we know that the mass number is 12. Now, we know the atomic number is 6, but we don't need this to tell us that, right? Because we know carbon has to be 6. So another way to write it is this. Why do we not need the 6 down here? Because it's understood that carbon has an atomic number of 6. These are the 4 ways in which we could designate the mass number. And you need to be able to understand how to find the mass number. Now, given the mass number, you also have to be able to figure out how many neutrons there are. Well, how do we do that? Well, let's think about it. What's the mass number? The mass number is protons plus neutrons. What's the atomic number? The atomic number is the number of protons. So if the mass number is protons plus neutrons, and the atomic number is just protons, What's the only difference between the atomic number and the mass number? The number of neutrons. So the way we figure out the number of neutrons is we take the mass number and subtract the atomic number. So in this case, the mass number is 12 minus the atomic number, or the number of protons, which is 6, which gives us 6 and 6 neutrons. So now we know that this specific substance, carbon-12, has 6 protons and also has 6 neutrons. And understanding how to figure that out will be very important in the next thing we're going to talk about. Because the next thing we're going to talk about are isotopes. And what an isotope is this two of the same elements with a different mass number. Now, if they're the same elements, they have the same number of protons. So if they're isotopes of an element, and they have a different mass, that must mean they have a different number of neutrons. And you're right, you do. Isotopes have the same number of protons and different number of neutrons. Let me give you an example of another isotope of carbon. We have carbon-12. We could also have carbon-14. Carbon-14 is an isotope of carbon. Carbon-12 is an isotope of carbon. It's just two substances that are the same element, so they have the same atomic number or the same number of protons, but a different mass number, so they have a different number of neutrons. Well, how many neutrons do we have in carbon-14? Well, let's figure it out. The mass number is 14. And remember how we find neutrons. We take the mass number and subtract the atomic number. The atomic number, did that change? Nope, the atomic number is still 6. And here, there are 8 neutrons. So in this isotope of carbon, there's 8 neutrons. And remember back here, it was 12 minus 6, which is 6 neutrons. So a lot of times the regent says, how do these two isotopes differ based on their subatomic particles? Well, the way they differ is that carbon-12 has 6 neutrons and carbon-14 has 8 neutrons. That's the only way they differ. That's it, based on the number of neutrons. And those are what isotopes are. And it's very important that you know how to find the number of neutrons, because that will give you a better idea of how to tell the difference between two different isotopes of the same element. Now, the next thing I have to talk about deals with isotopes. It's the atomic mass. Now, on the periodic table, they list the atomic mass. So let's show you in the periodic table how they list the atomic mass. The atomic mass you see for carbon, you probably can't see it that clearly, but you see it on the slide screen. The atomic mass is 12.011. That's the atomic mass for carbon. That's not the mass number, that's the atomic mass. What does the atomic mass represent? The atomic mass represents the average of all of the isotopes of a given element, which means that all the carbons that we found that naturally occur, all the carbons we found, if we took all of them and the ratios, the percentages of how much we found, the average of all those isotopes had a mass of 12.011. And if you look on the periodic table, almost every single element has an atomic mass with a decimal. Why are there decimal or fractional masses on the periodic table? Because the atomic mass is the average. And when you get the average, you get decimals. So it's very important that you understand that the atomic mass is the average of all the naturally occurring isotopes of a given element. Now, they sometimes ask, how can you determine the average atomic mass of an element? Well, you would need the masses of each of the elements and the ratios of its naturally occurring isotopes. So I'm going to give you a problem, and you also have to be able to calculate them. So I'm going to give you a problem right now. Chlorine. Chlorine, they could tell you that there's two isotopes of chlorine. Chlorine-35 and chlorine-37. Chlorine-35 has a mass number of 35. Chlorine-37 has a mass number of 37. And let's say they said that 75% of all of all the chlorines is chlorine-35, and 25% of all the chlorines has a mass of 37. You have to then be able to calculate the average atomic mass for chlorine. And the way you do it, now people get confused. A lot of students say, well, it's average atomic mass. I just add 35 plus 37 and divide by 2 because that's what I learned in math. Well, that doesn't apply because the ratios are different. It's 75% to 25%, and you have to take that into account. Now, these problems are so simple as long as you know how to do them. A lot of students don't know how to do them, so I'm going to teach it to you. You have to make sure you know how to do this. What you do is you take the mass number and you multiply it by the percentage. And then you add them up. So you take the mass times the percentage plus this mass times its percentage, and that gives you 100%. That gives you the whole entire atomic mass. How do we convert a percentage into a real number? Two ways. We can either divide it by 100, or the same thing is just moving the decimal point over 2 spots, whichever you're more comfortable with. So now we're going to do this one together. 35 times 75%, move the decimal point over, is 0.75. So we have 35 times 0.75 plus 37 times 0.25. Now, then we take 35 and multiply it by 0.75, and we get 26.25 plus, then we take 37 and multiply it by 0.25, and we get 9.25. We add them together, and what do we get? We get 35.5 AMUs. And the atomic mass for chlorine is 35.5. And if you see on the periodic table, the atomic mass for chlorine rounds to 35.5 because they calculated the same exact way we did. So it's very important to know how to calculate the average atomic mass. And you need to know that you multiply the mass times the percentage plus the mass times the percentage. And that gives you your average atomic mass. Okay. Make sure you know how to do these math problems because the Regents is notorious for giving math problems, and chemistry is a lot of math. So if you know how to do these, you'll get the questions right. And sometimes on the Regents, they don't ask you to calculate this answer. They ask you just to leave it in a form that shows you knew what you were doing. So if you don't have to calculate it, don't do it. It may just say show the correct numerical setup, and that's all you have to do. But make sure you add the 2 or 3 or however many isotopes there are. You add them up, and you get your atomic mass. The next thing we have to talk about are electrons, where they are and what that all means. Now, we know that electrons are in orbitals, regions of probable location, but what's also important to know is that each electron has a specific amount of energy, and that energy is designated by shells, electron shells. And things you need to know, that each shell can only hold a certain number of electrons. Each shell has a maximum number of electrons that it can hold. And the shells closest to the nucleus have the least amount of energy, and the shells further away from the nucleus have more energy. So as you get further and further away from the nucleus, each electron has more and more energy. And you need to know the first shell can hold 2 electrons. The second shell can hold 8 electrons. The third shell could hold 18 electrons. And you don't need to know more than that, but you need to understand that there's a maximum number of electrons that each shell can hold. How do we designate where the electrons are within the shell? We use something called an electron configuration. Let's say we want to take sodium. Sodium, you could see on the periodic table and you can see on the slide window that sodium has an electron configuration of 2, 8, 1. What does that mean? 2, 8, 1 stands for something. That means that there are 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell, in the outermost shell. There are 11 electrons in sodium, in a sodium atom, and this is how they are situated. They're situated in energy levels. The 2 electrons that are closest to the nucleus have the least amount of energy. The 8 electrons in the second shell have a little bit more. And the one electron in the third shell have even more. But that's the electron configuration. And the most important shell you can know about is that last shell. You see where it says 1? The electron configuration is 281. The valence shell is the outermost shell. And how many valence electrons does sodium have? It has 1. And how do you tell the number of valence electrons that any atom has? Well, you go to the periodic table, you look at the electron configuration, and the last number in the electron configuration designates how many electrons are in the valence shell, how many valence electrons there are. And valence electrons are very important because valence electrons gives the elements the properties of that element. So it's very important that you understand what a valence electron is. Now, all these electron configurations that we're talking about represent atoms in the ground state. Ground state means the electrons are closest to the nucleus and they have the least amount of energy. So 281 represents the ground state electron configuration for sodium. It has the maximum amount of electrons it can have in the first shell, which is 2. It has the maximum amount of electrons it can have in the second shell, which is 8. And it has 1 electron in the third shell. You have to understand, though, what happens when electrons gain energy. Because electrons can gain energy. How do they gain energy? Well, you heat them up. If you heat up a substance or an atom or a substance that you have, what happens? It gets hotter. And what happens to the substances in it, the part in it, the electrons? They gain energy. And you need to know what happens when they gain energy. When an atom gains energy, at least one electron, at least one, gains energy and gets what we call excited. Think about when you're excited. You have all this energy now, right? It's the same with an electron. When an electron gets heated or gains energy, that electron jumps to higher levels. Why does it jump? It jumps because it's going to the higher energy level. Each shell represents energy. The further away you go, the more energy you have. So in this case, we're taking a specific electron, and we're showing what happens when you add a flame. The electron, one of the electrons at least, gains energy and jumps to the higher levels. So what happened here is one of the electrons in the second shell jumped to the fourth shell. It gained even more energy. So now the electron configuration is 2. There used to be 8 electrons, but now there's 7. There's still 1 in the third, but now there's 1 in the fourth. So the electron configuration for this sodium atom in the excited state, in this specific case, is 2, 7, 1, 1. And there are a couple things to keep in mind. First, there's the same number of electrons, right? There's only 11 electrons in sodium atom, and there's still 11. It didn't gain electrons or lose electrons. It just got excited. The electrons gained energy. So that's what happened here. 2, 7, 1, 1. Also note that the maximum amount of electrons that each shell can hold doesn't change. But they don't have to fill the maximum. You could see that the second shell should have 8 before any electrons go to the third shell. But in this case, the electron from the second shell jumped even higher. Now, it could be any designation of this. It could be 2711 like it is. It could be 2711 would be right. It could be 2612. It doesn't matter. It just has to be out of order with the same number of electrons. That represents the excited state. But what happens when you're excited? Well, even when you're excited, eventually you lose all that energy. Well, same thing with the electrons. After a while, that electron that gained all that energy, that's in the fourth shell in this case, that electron actually gets tired. And what happens is it loses all of its energy. So what happens is, as it loses energy, where does it go? Well, it has to go back where there's less energy. It falls back down to ground state. As it falls back down to its original position, all that energy that it had, that it absorbed from the heat, gets released. Because there's still that energy there, but the energy gets released as the electron falls back down to ground state. And the energy gets emitted, and the amount of energy that gets sent out can indicate what element it is. And it's called something called the bright line spectrum. When electrons go back down to ground state, they emit energy or light in the form of spectral lines. And you could see sodium produces a yellow light, because they each produce color when they get sent down, but they also produce a bright line spectrum, which you could see sodiums look like 2 lines, 2 narrow yellow lines. in the middle, because that's sodium's bright line spectrum. So we know what an element is just when we heat it up, because we see that it produces a yellow color, which translates to two narrow lines on the bright line spectrum. And every element has a different designation, bright line spectrum. Look at hydrogens. Hydrogen is very different than sodium's. That's how we could tell hydrogen and sodium apart, by heating them up. That's the bright line spectrum, and that's what you need to be able to look at a bright line spectrum and determine what element it is based on comparing it to other bright line spectrums. And there are loads of questions you could do with this topic, and make sure you can do them and understand them, because it's important that you understand the bright line spectrum. Now, I want to summarize ground and excited state, because it's very important that you understand the ground and excited state. Ground state: electrons are closest to the nucleus, and they have the least amount of energy. That's the normal state. That's the state you find in the periodic table. That's the ground state. What happens is the atom absorbs energy. So the electron absorbs energy. And when it absorbs energy, the electrons jump to higher levels. Eventually, all that absorbed energy that the electron has eventually gets released. And when the electrons fall back down to lower levels, they release energy. And they release energy in the form of color. So you see color or spectral lines, and those spectral lines can designate what the element is. So you need to understand that when the time that you can actually see the color is when the electrons fall back from excited state back down to ground state, from the higher energy levels back down to the lower energy levels. And that's energy transition and understanding ground and excited state. And it's very important. You need to understand that. The last thing we need to talk about is the difference between an atom and an ion. It's very important, and a lot of students have trouble with this. And I think they have trouble with it because they hear these terms so often, but they don't completely understand what they are. So at Regents Tutor, we're here to make sure you understand it, and it makes it simple for you. So listen to what I'm about to say. An atom is neutral. An ion is charged. If you know that, you're halfway there. But you need to know at least that. Atom is neutral. Ion is charged. What does it mean to be neutral and charged? Well, what's the only thing within a substance, within an element, that has charge? Not a neutron. Neutrons have no charge. So we must be talking about the protons, positive, and electrons, negative. We are. In an atom that's neutral, the number of protons, the number of positives, equals the number of electrons, the number of negatives. So you know that in an ion, protons equal the number of electrons. In an atom, the number of protons equal the number of electrons. In an ion, which is charged, that's not the case. The number of protons do not equal the number of electrons. How does an atom become an ion? An atom becomes an ion by either gaining or losing electrons. Remember, you don't gain or lose protons because protons make you what you are. You can't, if a carbon atom which has 6 protons gained a proton, it wouldn't be carbon anymore. A carbon atom, though, can gain or lose electrons and still be carbon. And you need to understand what happens when you gain electrons. Now you have to think, electrons are negative. Okay, if an atom gains an electron, what happens to it? It gains a negative. It becomes a negative ion. If an atom loses an electron, well, it still has the same number of protons, so if it loses an electron, it's positive. So you need to understand that. And I'll show you, I'll illustrate that for you right now. Carbon has, in an atom of carbon, has 6 protons and 6 electrons. So it has 6 positive charges and 6 negative charges. If it gained an electron, it would have 7 negative charges, so it would be -1. Let's say it lost an electron. So now it would only have 5 negative charges, but still that's 6 positive, so it would be +1. You need to understand how something is positive or negative. If it gains electrons, it gains negatives, it becomes negative. If it loses electrons, it becomes positive. And let's do an oxygen 18 negative 2 ion and talk about how many protons and electrons there are? Well, we know it's oxygen, and if we're saying it's oxygen 18, we also could tell how many neutrons there are. So let's, for the fun of it, do the protons, the neutrons, and the electrons. Protons. If it's oxygen, you go to the periodic table, you look for the atomic number, you see it's 8. That's it. It's 8 protons. That's easy. Protons is 8. If it was an atom, how many electrons would there be? Well, there would be 8. But it's not an atom. It's a negative 2 ion. Since it's a negative 2 ion, we have to do something different. If it has 8 protons, and it's a negative 2 ion, that means it gained 2 electrons. It has 2 extra electrons than protons. Therefore, the number of electrons has to equal 10. 10 electrons. Because there's 2 more than there are protons. 2 more negatives than there are positives. And neutrons, we know, mass number minus atomic number, 18 minus 8 is 10. So in this case, oxygen 18 negative 2, 8 protons, 10 neutrons, and 10 electrons. And just keep in mind, if it was a positive ion, there would be less electrons. So if it was, and I'll do one for you actually. Let's just do one just to show you, and then we'll be done. So if we have sodium with a +1 charge, let's just do protons and electrons. Let's not even worry about mass number. Well, sodium has an atomic number of 11, which means there are 11 protons. If it's a positive 1 ion, that means there's 1 more proton than electron, which means that sodium lost 1 electron, which makes it 10 electrons. And you should be able to always tell the number of subatomic particles in any substance you're given, because the Regents loves to talk about this, and you need to understand it. So we talked a lot about atomic structure here. You learned a lot of different things. Now, after you're done with this lesson, very important that you go over all the questions that relate to atomic structure. Now, you can get them right or wrong. I don't care. Obviously, I want you to get them right. But what I want you to do is I want you to go over every question. Even if it's wrong or right, I want you to listen to the Regents Tutor video explanation. I want you to hear your Regents Tutor explain every question to you. Because the more you go over it and the more repetitive it is, the more it's going to stick in your head. Look over the review sheet, come to the chats, go over the lesson again, pause, rewind, and do whatever you need to do, but make sure you understand atomic structure. Hope you learned something. I think you did.